In an organic reaction, when reactants react to form a new compound, the reactant that supplies the carbon atom for the formation of a new bond or to the reactant on which the focus is called the substrate, whereas the other reactant in the reaction is called the reagent. In the reaction between chlorine and methane, methane supplies the carbon atom to form chloromethane. Hence, methane is the substrate, and chlorine, the other reactant, is the reagent. Covalent bond between carbon and bromine of methyl bromide gets cleaved and a new bond between carbon and hydroxide ion is formed. The energetics during breaking and forming of bonds, movement of electrons, and the rate of reaction in a sequential description are referred to as the reaction mechanism. Let's study each step in detail. A covalent bond can get cleaved either by homolytic cleavage or by heterolytic cleavage. In homolytic cleavage, a bond breaks equally in such a way that each atom gets one electron of the shared pair. A fishhook or half-headed arrow is used to show the movement of a single electron. Homolytic cleavage results in the formation of neutral atoms or groups with one unpaired electron. These are known as free radicals. The free radicals thus formed are highly reactive due to the presence of unpaired electrons. For example, the homolytic cleavage of the chlorine-chlorine bond in chlorine molecules, induced by heat or light, leads to the formation of two chlorine free radicals. Depending on the number of alkyl groups directly attached to the carbon free radical, alkyl free radicals are classified as primary, secondary, and tertiary. Greater is the number of alkyl groups, greater is the stability. Hence, primary alkyl radicals are the least stable, while tertiary radicals are the most stable. The organic reactions preceded by homolytic fission producing free radicals are called free radical or homopolar or non-polar reactions. Heterolytic cleavage is just the opposite of homolytic cleavage. In heterolytic cleavage, a bond is broken unequally, and the shared electron pair goes to the more electronegative atom. Thus, after heterolytic cleavage, the atom that loses the bonded electrons gets a sectet, electronic structure, and acquires a positive charge. For example, in the heterolytic cleavage of bromomethane, the shared electron pair goes to the bromine atom, leading to the formation of a bromide anion and a methyl cation. A positively charged carbon with a sectet, which is the methyl cation here, is called a carbocation or a carbonium ion. Carbocations are very reactive as they have a strong tendency to complete their octet. Depending on the number of alkyl groups directly attached to the positively charged carbon, Carbocations are classified as primary, secondary and tertiary carbocations. For example, ethyl cation is a primary carbocation, while isopropyl carbocation and tert-butyl carbocations are secondary and tertiary carbocations respectively. Stability of the carbocations increases with increase in number of alkyl groups bonded to the carbocation. Hence, primary carbocations are highly unstable, while tertiary carbocations are the most stable. In methyl carbocation, 3 sp2 hybridized carbon orbitals overlap with the 1s orbital of each of the 3 hydrogen atoms. The remaining 2p orbital of carbon is vacant and lies perpendicular to the molecular plane. Therefore, the shape of the carbocation is trigonal planar. There are also heterolytic cleavages where the carbon gets the shared pair of electrons. For example, the removal of the hydrogen ion in the presence of a base from the methyl part of an acetaldehyde molecule leaves both the carbon-hydrogen bond electrons on carbon. Such a chemical species bearing a negative charge on carbon atom and possessing 8 electrons in its valence shell are called carbanions. Carbanions also are classified as primary, secondary and tertiary carbanions, depending on the number of alkyl groups attached to the negatively charged carbon. Stability of the carbanions decreases with increasing number of alkyl groups bonded to the charge-bearing carbon atom. Hence, tertiary carbanions are highly unstable, while primary carbanions are the most stable. The shape of a carbanion is tetrahedral. All the organic reactions preceded by heterolytic bond cleavage are known as ionic or heteropolar or polar reactions. Polar organic reactions are caused by 2 types of reagents: electrophiles and nucleophiles. Electrophile is an electron-seeking or electron-loving species, as it is electron deficient. Electrophiles may be either positively charged, such as carbocations, hydrogen ion and hydronium ion, or electrically neutral species such as boron trifluoride, aluminium chloride, ferric chloride and carbonyl group. A reaction initiated by an electrophile is called an electrophilic reaction. Electrophiles always attack the substrate molecule at the site of maximum electron density. An electron-rich reagent that donates electrons to the positive or electron-deficient site in a compound is called a nucleophile. A nucleophile is a nucleus-loving species, as it is electron-rich. Negatively charged species with lone pairs of electrons, such as hydroxide, chloride, cyanide ions and carbanions, and molecules such as water, ammonia and lithium aluminium hydride are some of the neutral nucleophiles. A reaction initiated by a nucleophile is called a nucleophilic reaction. Nucleophiles always attack the substrate molecule at the site of minimum electron density. The movement of an electron pair in organic reactions is denoted by a curved arrow. The curved arrow starts from the point where an electron pair is shifted and ends at the final location where the pair of electrons may move. For example, electron flow from a pi bond to the adjacent bond position, or from a pi bond to the adjacent atom, or from an atom to the adjacent bond position may be represented as follows. You have already learned that most of the attacking reagents carry either a positive or a negative charge. Hence, for a reaction to take place on the substrate, it must possess oppositely charged centers. This is made possible by the partial or complete displacement of the bonding electrons. The factors which influence the electron density in the substrate are inductive effect, resonance effect, electromeric effect, and hyperconjugation. Let's understand each type one by one. In the case of a covalent bond between two atoms of different electronegativity, the electron density shifts more towards the more electronegative atom of the bond. The electron shift polarizes the covalent bond, leading the more electronegative atom to acquire a partial negative and the less electronegative atom to acquire a partial positive charge. The fractional electronic charges in a polar covalent bond are denoted by delta positive and delta negative, and the shift of the electron density is shown by an arrow that points from delta positive to delta negative end of the polar bond. For example, in chloroethane, chlorine is more electronegative than carbon. Hence, the electron pair shared between carbon and chlorine is displaced towards the chlorine atom. Thus, a partial negative charge is acquired by chlorine and a partial positive charge is acquired by carbon. The partial positive charge on C1 draws some electron density towards itself from the adjacent carbon-carbon bond. This causes C2 to acquire a small positive charge. The delta plus represents a relatively smaller positive charge as compared to that on carbon 1. Thus, carbon-chlorine bond induces polarity in the adjacent bonds. Such polarization of a sigma bond caused by the polarization of an adjacent sigma bond is called inductive effect. Inductive effect decreases as the distance from the source atoms increases. The inductive effect is related to the ability of a group to either withdraw or donate electron density to the attached carbon atom of the alkyl group. If any atom or group attracts electrons more strongly than hydrogen, it is classified as electron withdrawing group and is said to have a minus inductive effect. On the other hand, if any atom or group attracts electrons less strongly than hydrogen does, then it is classified as electron donating group and is said to have plus inductive effect. Halogens, nitro, cyano, carboxy and ester groups are electron withdrawing or minus inductive effect groups. Alkyl groups, for example, methyl and ethyl, are electron donating or plus inductive effect groups. Now, let's learn about another important electronic effect called the resonance effect. Resonance refers to the phenomenon where two or more structures can be written for a molecule or an ion. Because of resonance, the electronic charge spreads over the entire molecule and hence affects its polarity. If the polarity of a molecule is developed either by the transfer of electrons between two pi bonds or from a lone pair to a pi bond in conjugation, creating high and low electron density due to resonance, then this phenomenon is called the resonance effect or mesomeric effect, which is designated as R or M effect. Resonance effect is of two types. They are positive resonance effect and negative resonance effect. In the positive resonance effect, the transfer of electrons is away from an atom or substituent group attached to the conjugated system. Halogens, amino group, hydroxyl group, and methoxy group are some of the examples of positive resonance effect groups. The positive resonance effect in monosubstituted benzene increases the electron density at ortho and para positions. For example, in aniline, due to the conjugation of lone pair of electrons on the nitrogen of the amino group with the pi electrons of benzene, the electron density is increased at the ortho and para positions as shown here. When the electron shift takes place in the direction of the atom or substituent group attached to the conjugated system, it is called the negative resonance effect. Nitro group, cyano group, and carbonyl group are some of the examples of negative resonance effect groups. The negative resonance effect decreases the electron density at ortho and para positions in the molecule. For example, in nitrobenzene, as nitrogen withdraws electron density from the ortho and para positions in the benzene ring, the electron density decreases at those positions as shown here. Now, let us look at the electromeric effect. It is a temporary effect and observed only in organic compounds with multiple bonds in the presence of an attacking reagent. Electromeric effect may be defined as the complete transfer of the shared pair of pi electrons of multiple bonds to one of the atoms in the presence of an attacking reagent. It is important to note that this effect ceases to exist as soon as the attacking reagent is removed from the domain of the reaction. This effect is represented by E, and the shifting of the electrons is shown by curved arrow. There are two types of electromeric effects, positive and negative. In the positive electromeric effect, the pi electrons of the multiple bond are transferred to that atom to which the attacking reagent is bonded. For example, in the addition of acids to alkenes, the pi electrons of the double bond are transferred to that carbon to which the attacking reagent is bonded. On the other hand, when the pi electrons of the multiple bond are transferred to the atom to which the attacking reagent does not get attached, it is called negative electromeric effect. In the addition of cyanide ion to alkenes, the pi electrons of the double bond are transferred to that atom to which attacking reagent does not get attached. Let's learn what hyperconjugation is and how it affects the stability of the various species in detail. A general stabilizing interaction which involves the delocalization of sigma electrons of a CH bond of an alkyl group directly attached to an unsaturated system or to a species with an unshared p orbital, such as carbocations or free radicals, is known as hyperconjugation. Hyperconjugation is a permanent effect. Let us take the example of ethyl carbocation to explain this effect. In ethyl cation, the positively charged carbon atom has an empty p orbital. One of the carbon-hydrogen bonds of the methyl group aligns in the same plane with the empty p orbital of the positively charged carbon atom. The electrons of this carbon-hydrogen sigma bond then get delocalized into the empty p orbital as shown here. In carbocations, this delocalization of electrons helps in dispersing the positive charge on the carbocation to the adjacent atoms and stabilizes it. Thus, the carbocation is stabilized by hyperconjugation. Greater the number of alkyl groups attached to a positively charged carbon atom, greater is the hyperconjugation interaction and stabilization of the cation. Hence, the tertiary carbocation in which there are 3 alkyl groups attached to the positive carbon is more stable than a secondary carbocation with 2 alkyl groups. Similarly, a secondary carbocation is more stable than a primary carbocation. Therefore, the order of stability decreases from tertiary carbocation to methyl cation. Hyperconjugation also explains the stability of certain olefins over other halides. For example, propene is more stable than ethene because in propene there are 3 HC hyperconjugated bonds which lead to greater stability. If you observe the resonating structures of propene, you can see that there is no definite bond between the carbon atom of the methyl group and one of the hydrogen atoms. Hence, hyperconjugation is also known as no-bond resonance.